We have Dr. Panda talking about new ways of accelerating big data, Hadoop, and Memcached.
Okay. Good morning again. So let's get started. For the last 2 days, we heard a lot about MPI and how to take advantage of designing high-performance MPI for the high-performance networks like InfiniBand. And just a quick recap, we saw about MPI, different features of MPI. I introduced the MapIS2 stack, talked a little bit about MPI for exascale systems, and how we are taking an approach to enhance and strengthen MapIS2 for exascale systems. So here we'll change the gear a little bit, and this is some of the things what we have been doing since last year. And the example, if I remember, I gave you yesterday saying MPI library is a car. Okay, so we are designing a car, and we have seen that we can really design a very nice car while taking advantage of all these new features. So now let's ask the question saying, can those techniques be applied to something else, like let's say bus? Yesterday I said truck, but let's assume the bus. Okay, think of like a bus for the transportation in a city. Of course, the bus and cars, there are some similarities, but there are a lot of differences. Okay, you cannot just take the engine from a car and then put it in a bus and expect that it will work. Okay, because the bus has so many other components, its characteristics are different. A car has like 4 to 6 people. Bus has to be designed for 60, 80 people. Bus makes frequent stops. So all kinds of differences are there. And that's what this talk will be focusing and saying what are the differences and how exactly we want to take the high-performance networking technologies like InfiniBand and its features to this big data area. Okay. So these are just like some trends. Most of you are familiar, like the top 500. We are seeing these high-performance networks are gaining a lot of traction. This is like the InfiniBand which started in 2002, is gradually going up and up. This is like the number, and this is in terms of the total performance share. And especially the Open Fabrics software stack has been a very big drive for this entire field, not only with InfiniBand, but iWarp and Rocky. So these are all helping for the software stacks for the high-performance systems. And we have designed like MPI and parallel file systems. Now, if you remember like the InfiniBand's introduction as a standard and then coming up in like the 2000-2001 time frame, almost 11 years have passed, 11 and a half years. Okay, this is like a decade. So a lot of decades of research have gone into designing these high-performance MPI stacks and parallel file system stack, okay, which we see these days being used on many systems. And myself and also several other talks also focus saying that there is also newer programming models are coming, like UPC, OpenSMAM, hybrid. So these are again like some divergence from the main track. Now, if you take a look at the performance, what has happened over these 11.5 years, so these are some of the InfiniBand adapters over the years, and this is the MPI latency I'm trying to show. So these are like the different both Mellanox cards as well as QLogic cards. So you have the QLogic DDR, QLogic QDR, ConnectX DDR, ConnectX2 with the PCI Express 2 DDR, and very latest one is the ConnectX3 with PCI 3 FDR on the Sandy Bridge system. Okay, so this is trying to show the small message latency. The only difference here is that the data is not complete. This number which has been taken on Sandy Bridge with Intel PCI Gen 3 without the IB switch. So I just want to clarify that. The switch will add a little bit of delay. I didn't have the complete environment with me. So here if you see, like we have been steadily going down, and this latency is like 0.8 microseconds. Okay, so the latency to send a small data from one node to the other node, so now we have gone below 1 microsecond. The switch will add actually a little bit of delay here. And this is the latency for the large messages. And we are seeing like with continuously from DDR to QDR to FDR, of course, as the message size increases, you will see better latency because there is a fat pipe and we are trying to send the large data there. And this one is the same thing with bandwidth. So now you can see with the latest FDR, you can get very close to 6 gigabytes per second at the MPI layer. So this is one-sided. And the bidirectional bandwidth comes to very close to 11 gigabytes per second. Okay? So these are the kind of things I'm just trying to show you some numbers to get a feel for what has happened over the last several years in this field. And that is actually helping for people to actually design these large scale systems, and we know that like a lot of IB clusters these days are in the top 500 list. In another few months we'll see the new June 2012 list, and people are deploying all kinds of large scale 100,000 core systems. And so now basically it is a multi-core technology with high performance InfiniBand and with open source, open fabrics software stack that is helping people to enjoy the benefits of deployment of very large clusters. But now let's change the gear, okay? So these are all for scientific computing, okay? But now we know, like let's say we are focusing on enterprise computing or commercial computing, there's huge amount of data, okay? I mean, these are all kinds of e-commerce applications, data mining, data warehousing, all kinds of banking transactions we do, airlines. People always want to find out like what you are doing, right? That is the end goal, okay? If a company can find out what you are doing, they can really target a lot of stuff to you. That is the end goal of many of these companies, okay? So here we are talking about this big data, okay? Not only like from a search perspective, but if you take a look at like Facebook, I think I read somewhere what like they have 96 petabytes of data now, okay? They just like I read somewhere, I can't prove it, but this is how we are seeing like all kinds of pictures, videos, and all everybody is trying to share. So the world is in a very different place than it was 10 years back. Okay? So in this kind of environment, so people are trying to take a look at newer kind of middleware and see how those kind of a middleware can be designed to provide performance and scalability. Okay? And some of these are here, like the Hadoop, which I'll be talking a little bit more, is a open source software. It has different components, HDFS, HBase, MapReduce, as well as Memcached. So you can think of like these are the middlewares just like MPI for scientific computing. Okay? And if we have achieved designing a high performance MPI, so why can't we do it on this side? Okay? So that is the the car and the bus analogy I'm trying to give. So now let's say ask the question saying, what are the big issues? Okay? So if you take a look, most of the current enterprise systems use 1 gig E. Okay? So it is like if you think of the bus, they are running with a very old engine. Okay? Now, of course, if you run an old engine, I mean, you can't drive very fast. So there are performance issues. You cannot put a lot of buses all around the city to transport people. So there are scalability issues. And but once people are seeing that these high performance networks are helping, especially in the scientific computing domain, so there is a lot of interest coming now. Okay? And especially if you attend a lot of these talks, Oracle, IBM, Google, everybody is working in those directions, trying to explore how we can take advantage of these modern networks for their environment. Now the question is, what are the challenges? And where do these bottlenecks lie? I mean, just like I said, the example earlier, can I take the engine from the car and just plug it in there? Will it work? I don't think so. Okay? So it needs to be redesigned. And that's what I'll try to outline, saying what are the components which need to be redesigned and what kind of performance benefits you can expect to get. And so the broad goal is that can these bottlenecks be alleviated with new designs similar to the designs adopted for MPI. So the outline of this presentation will be as follows. So first I'll try to just introduce architecture of this middleware. Many of you might not be familiar, especially I'll go over 3 things: Hadoop, Memcached, and HBase, which is a component of that Hadoop. And then I'll be trying to go into much more details outlining these challenges. How can we accelerate this middleware? And especially try to focus on 3 components, and I'll show you like what kind of designs you can do and what kind of like case studies, what kind of performance you can get. Okay? And then conclude. So first let's talk about Memcached. Okay? So many of you might have seen this kind of architecture, which is called the enterprise data center architecture or e-commerce architecture, multi-tier data center architecture. People use all kinds of terminology. So there are typically like some front-end servers, Then there are some intermediate like servers. These could be business logic. Then you have the database servers. Okay. So take an example of like Amazon.com. Okay. So as soon as you log on Amazon.com, your request goes into one of these front-end servers. Okay. And if your information, whatever book you are searching for, you type it and then say search. If that information is available or being cached in one of these nodes, then immediately you will get a response back. Okay. If not, your request may get moved to the intermediate tier, and then again that kind of logic continues. And in the end, or through that process, you might have seen, you get a lot of messages like saying, okay, person X or this book was liked by these people, they also liked book Y and G. So those kind of things also get analyzed and then being forced to you, saying that, okay, you might be interested in buying those kind of other books also. And finally, if you want to actually buy that book, your request gets moved to the database servers and the transaction takes place. So you give the credit card and the replies actually come back and says, thank you, you'll get the book in by this mail, confirmation number, and in a few days. Okay, so that's how typical transactions go. Okay. And so broadly, if you see this kind of environment, like a bunch of servers connected with high performance networks, and are no different than the regular clusters or scientific computing what we are talking. Physically, they are the same. There's a bunch of servers connected with high performance network. And here, there are different components which play a role here. So one of the components is called Memcached. So the idea here is that like if you take a node, and gradually I'll introduce these different components, like we have the CPU, the memory, hard disk drives, SSDs. So you take memory from all of these nodes and then try to put it together to come up with a big cache. And that's what is called Memcached. Okay? And this is a very integral part of the Web 2.0 architecture. So basically you can think of like it's a distributed caching layer. So it allows to aggregate spare memory from multiple nodes. So let's say you have 16 nodes here. Each one is contributing 2 gigabytes, so you have a 32 gigabytes of space. Okay? And there you can actually put a lot of information, like the queries from the previous, the results from the previous queries you can hold there, or you can results of some API calls you can hold there. Okay? So it's just like a cache. I mean, just like the CPU memory hierarchy, we always try to keep the latest information on the cache so that we can very quickly get hold of it. The same kind of thing happen also here. So this is a scalable model in the sense, like I can keep on adding more servers and they contribute memory and then we can get a bigger cache. But now if you see the actual transactions, when some request is coming, and since it is a combination of memory and they are connected with high performance networks, so there will be a lot of network transactions to find out where the data is and to get that data and then to reply back to the client. So these kind of operations are typically network intensive. Okay. So this is where it comes, like if we can take advantage of the modern networks, can we really accelerate this? Okay. So that is the kind of goal which we are trying to solve here. Now let's take a look at the Hadoop architecture. Okay. So this Hadoop architecture, again, it was like initially proposed by Google, and the underlying thing is called an Hadoop distributed file system. So they have a lot of naming conventions, like there is something called a name node, there are some data nodes. And there is an inherent fault tolerance here in the sense, every time some write takes place, not only you keep one copy, you replicate it. So there are some degree of replication. You can define like a 2, 3, mostly 3 is the most commonly used one. So you try to keep redundant copies. So if some node dies, then you should be able to recover. And then we have a concept of like data nodes, which stores the blocks and hosts the, like many of you might have known about the map reduce style of computation. So there is a mappers, there are reducers, so you try to assign those mappers and reducers in a distributed manner and get the data very quickly, and then provide the solution to the client. So then there is a job tracker which tracks the jobs and detects the failure, and this model scales, but if you take a look at internally, you will see there is a high amount of communication is happening between each of these phases. Okay, it is a scalable architecture, but when you try to put a lot of data with a lot of nodes, these transactions happens over the network. That's the only network where things are moving, and that becomes the bottleneck sometimes. So in a pictorial manner, I mean, that is the overall architecture, but if you see what is actually happening in the network level interactions between the clients and data nodes, so broadly you can think of these are HDFS clients, and these are the HDFS data nodes, and they can have like hard disk drive or SSDs or a combination of those things, but basically these clients are interacting with the data nodes over this high performance network, okay, and that's what will be the focus again in this talk. The third one is the HBase, and it is basically it is an open source database project. Again, it is based on the Hadoop framework, so at the lowest level is your Hadoop, as we saw earlier, but here it is basically the database, and it has also similar to Hadoop, it has a HBase master, there are some region server, there are some HBase clients, and typically they try to align, like if you have data is distributed, then when you are also searching, you are trying to put those region servers also on the different nodes, so you try to exploit the data locality and then do the search and give the results back. Now if we see from a network level interaction perspective, this is how it will look like. So these are HBase clients, then these are called HBase region servers and the data nodes. Okay. Again, the same concept comes here, like the high performance networks are sitting in between the servers to move those different kinds of queries or operations. Okay. So I'm trying to present it in a very simplified manner. I mean, there are so many components here in each one of these architecture, but we can take a look at this broad high level picture. So now if you take a look at these things, so what are the challenges then? Okay, if we want to accelerate these things. Now if you remember in my MPI talk, I gave a big picture, okay, at the multiple layers, and I don't want to repeat that, but I'll show a corresponding one here, okay? And the issues you will see are very similar. So first of all, now we are having all kinds of multi-core, many-core architectures with accelerators, so that is again a component given to us. We want to use that. Of course, the networking technologies are there, starting from InfiniBand to 40 gigi or 100 gigi or RNICs or whatever things are there. The third component, which we didn't talk, especially in the MPI domain, but becomes very important here, is the storage technologies. Because here we are talking about large-scale data, and eventually they get stored somewhere. And I'll show some very nice, interesting interplay between high-performance networks and storage technologies. Okay. Towards the end, I'll show how they can interplay. Then from the top level, think of like an application, like just like I said, like a Amazon application, like you're buying a book, or you can think of like buying an airline ticket or doing some search. So those are the end applications. Now, these applications, of course, they use this kind of the middleware. Just like for the scientific computing, you have end applications, you are using MPI as a middleware. So here we are using the end applications on top of these middleware like HDFS, HBase, MapReduce, Memcached, etc. Now, of course, these middleware, then the question is, okay, they need to be written. And so far they have been written with sockets. Okay, that is the most easier one over the years, like always things start with sockets and they have been written with sockets. And to make the matter a little bit worse, many of these components are written with Java. Okay, and obviously the biggest advantage is that it was written with Java for portability, but many of you know if you have played around with Java, they don't go well with performance. Okay, and this is the big challenge which we have been seeing also. If it would have been written in C and C++, I mean, things should have been much more easier. Okay, so now the question is, okay, if we want to deliver the best performance here, just like the MPI's layers I talked about, so we need to take advantage of all these technologies and then push the performance to this layer. Either we keep the sockets or we replace the sockets, okay, with better high performance like a verbs, those kind of stuff which I'll be talking. Then the communication and I/O library will look something like this. Okay, even the MPI stack I had outlined a lot of boxes. So here also we'll see like you have to accelerate the point-to-point communication because a lot of these nodes talk point-to-point. There are no collective communication concept here, but there are a lot of concepts in threading models because on each of the nodes, especially with multi-cores, you try to run a lot of threads. So how you actually support those threads, how you synchronize those threads, so those becomes the issue here. Then of course, as I said, like based on your storage technologies, the I/O and file system also plays a big role here. Okay, because you would be eventually you will be operating on the data which may not be in your cache, and then this is where you want to move the data, and if that becomes the bottleneck, you cannot even accelerate the other components. Then obviously like quality of service, That is also becoming increasingly important in this area. Just like all of us fly, and we know like the frequent flyer concept. If you are a gold, a diamond and all, you get like special lanes, special priority. All these enterprise servers, they also want to provide similar kind of services. If you have bought a lot of books from Amazon, the next time you log on, the system detects you, and your request or your transactions will get run faster compared to somebody else who is just simply browsing. So they want to bring those kind of QoS concepts to the data center environment. And of course, fault tolerance is very important here, because because these are designed on commodity components and you don't want to lose money. Many times you might have heard it, sometimes the news comes saying there was some catastrophic failure, Amazon lost so much money, all these kind of news come. Okay. So now, do you see a similarity? Like if some of you attended the previous talks, you will see the challenges are very similar to what is happening in the MPI or the scientific world. Any questions until this time? Yes, no, don't care. Okay. So now let's switch the gear and then see what is happening on the open fabrics. Okay, this is a very comprehensive slide which actually talks about all the things, what is happening in the open fabrics. Okay, let me explain that. Okay. So if you think of like the application, so now there are two ways you can try to write the application, either with the sockets, okay, so when I say application, it is very generic. It could be application or any middleware. Okay, it's not just the end application, any layer of the stack. Now, if you have written the sockets, traditionally, of course, we have there is the application interface, protocol implementation, network adapter, network switch. So this is the traditional TCP/IP path with Ethernet driver, Ethernet adapter, Ethernet switch. Okay, so that is either you use 1 gig, 10 gig, 40 gig. So this is the path you go. Okay. And with InfiniBand, we have been hearing, like yesterday Todd also mentioned, like there is IP over IB, which is the emulation of the IP. So here again, the same applications written with sockets can go over InfiniBand adapter and InfiniBand switch. Okay. And then of course with sockets, instead of like going through the kernel-based support, you can have some hardware offload, Ethernet adapter and Ethernet switch, and this is called the 1040 gig TOE. Okay, the solutions from like Chelsea or Net Effect, which has been acquired by Intel. So most of the sockets-based applications remain on this side of this chart. And what it allows you to run these applications if the application has been written with sockets, you directly run on these environments. So the applications don't have to be modified. Okay, so you deploy a cluster with any of these technologies or protocol combination, it will run. Whether it will give you the performance or not, that's a different story. Okay. So that is on this side. Now there are of course some intermediate solution has been proposed, which is like the sockets direct protocol or SDP stack. Some of you might be familiar. So here it again takes the similar approach, but now it takes actually the advantage of RDMA in the InfiniBand and try to accelerate it through the SDP stack. So this can actually run with the InfiniBand adapter and InfiniBand switch. Okay. So here again, it allows to run the same applications without any modifications. The same sockets, but it's trying to accelerate through the SDP stack. Now, so these are the left hand side. Now the right hand sides are the different approach in the sense the applications need to be actually rewritten, or some layers of the applications need to be rewritten, and instead of like sockets, let's say you go through the verbs. Okay, and especially in the Open Fabric stack, I mean things have been unified from both from InfiniBand side as well as from iVerb side. And if you see here, like this is you take advantage of all the RDMA and all the features of InfiniBand, user space, you run it over InfiniBand, adapter and switch. Okay, so that is the traditional InfiniBand support which we have been talking, whether it's an MPI or file system. So this is the best performing, best scalability solution. Now there is also, so similar kind of things are there also the iVerb, so that means you go through the verbs, the iVerb, user space, you go through the iVerb adapter, iVerb switch. And for the last few years, you must be hearing about this traction which is going on called Rocky. So what it does is the similar kind of verbs, but it goes through the RDMA user space, but it goes through the Rocky adapter and the Ethernet switch. Okay. So this actually comprises of all the network protocol switch combinations, whatever is available these days. Okay. So now from the enterprise side, what is happening is like people have been doing, traditionally they have been doing this. Some solutions are available here, but the question we want to ask is that can we really go to this layer? Okay? And of course, if we can have a solution here, this will also run over this layer as well as this layer. Okay? So that's what I'll be focusing over. So with that kind of a bigger picture, so now trying to abstract it a little bit in an easier manner. So this is the left-hand side I was showing, like applications, they're written with sockets, and they can run over 1, 10, 40 gig network. Now there are solutions like SDP, or some, you must be hearing about a lot of Hadoop accelerator kind of things from all different organizations. So there are solutions here to accelerate those sockets, and they can run over VERS or some hardware offload. It can be 10 gig or InfiniBand. So this is also an enhanced design. Okay? But what we are trying to ask the question here, that can we actually go to this kind of design? Okay? Because in this design also, sometimes you will see that since they are based on sockets, there is the stream semantics of the sockets might have a mismatch with the upper layers like Memcached, HBase, or Hadoop. Sometimes you may not be able to also achieve zero copy, which is very fundamental to like InfiniBand or any of the high performance networks. So we asked this question almost like last year, saying can we take our applications, can we provide some new designs which can directly run over VERS? Okay? And if it can run there, then it can run natively over InfiniBand or IORP, Rocky, whatever you call it. Okay. Now, in addition to that, when we started working on, and I'll show some results later on, because a lot of these applications are data intensive, it also has some interplay with the storage. Now, many times when we started doing some initial experiments, we saw that no, whatever you do with the network, you don't see the benefit. And some other people also in the community have indicated that, and then they argue that 1 gig is the best. Okay? But I'll show you some numbers that it's not because of the network is not good, but it's the storage is the bottleneck. Okay? Like the traditional systems, the current generation enterprise system use the traditional hard disk. Okay? Now if the hard disk is the bottleneck, then doesn't matter like how you enhance the stacks and what kind of networks you provide, it is limited by the hard disk. But as soon as you replace that hard disk with the solid state, the SSDs, then we started seeing the differences. Okay? And I'll show some concrete numbers. So what I want to keep this in mind here, that all the SSDs and other storage technologies are emerging, and does it change the landscape? And that's what we'll see. Over the years, you actually cannot keep, it's the example of the bus I said, you cannot just take the engine and then replace and then expect it to run, because the tires might be very old. Okay? So you need to replace it with a high performance tire. Together with the engine, then only you can have a very good bus design. Okay? Any questions so far? Come back from a coffee break. Everybody is silent or tired. Okay. The third day, so it's tired. Yeah. So let's continue and see some of the solutions. So what we did is we started with the initial thing is a Memcached. So I had described the Memcached architecture earlier. So in the original Memcached architecture, it was only the like sockets client. So what we introduced like a RDMA client. The client side, we introduced an RDMA client support. And here also, instead of just sockets worker thread, we also introduced some VERS worker thread. Okay? And then there was like the master thread, and then the server and the client perform a negotiation protocol, and then the master thread assigns the clients to the appropriate worker thread. And once a client is assigned a VERS worker thread, it can actually communicate directly and bound to that thread so that they can talk in VERS. And we also provide backward compatibility, so that if a client is, the traditional client is talking with sockets, it can still work. It's not just that you have to totally replace. And all other, the data structures of the Memcached are shared among the RDMA and sockets worker threads. And the important thing is the Memcached applications, they don't need to be modified. Okay, so because we are talking about a middleware here. So if some application was written with Memcached, we are not touching those. It's just the Memcached which is being modified. So you can just recompile, and then your application will run. And it can actually, Memcached server can serve both socket and VERS clients in a simultaneous manner. So I'll show you some numbers. So what we did is, we had two kinds of cluster. One is a little bit older cluster. There's an Intel Clovertown cluster with IBDDR. Then there is an Intel Westmere cluster with QDR. And we basically, I'll show you the numbers here, Memcached server 1.49, Memcached client. So these are all public versions you can download. And since we didn't modify anything, so we can actually take the numbers with the unmodified versions. And in all these experiments, since we are focusing on the network part, the way we configured, like the Memcached has something called a mem table, and that we made sure that it is contained in memory. That means no disk accesses are involved. So we are trying to isolate the effects and trying to study the benefits one at a time. Okay, and then later on we can put it all together and then show the complete benefits. So now let's take a look at some of the initial numbers. So this is like the Memcached get latency. So that means we are trying to get a data from that Memcached architecture. And this is a small message, so it is trying to show those. This is on the IB DDR, and this is the QDR cluster. So there are different lines here. So if you see here, like this is the 1 gigi line here. Okay. Then we have the 10 gigi. So this is the 10 gigi Chelsio with TOW. Then we have the IP over IB line here, and this is the SDP line here. And these are our new designs. What we have done, the OSU design. And we have two designs, and then we'll show the hybrid design, which is based on RC and UD. So this is here. You will see that now the Memcached is running completely over the verse, okay, with RC or UD. And if you see some of the benefits here, like let's say 4 bytes get latency, either with like RC and UD, there are some small differences. Like here we can give you like around 6 microseconds or 4 microseconds. You can finish this Memcached operations. On the DDR, they are around 12, and QDR, it's around 8 microseconds for 2 kilobytes. And if you take a look at it, compared to like a 10 gigi TOW for 2 kilobytes, we are almost giving a factor of 4 improvement. Okay. And since it's a DDR cluster, you need to make sure like the DDR is like the 16 gigabits per second, which is the actual, not the 20, which is the physical, but the payload we are comparing with like 16 gigabits per second. So the Memcached latency for large messages, we see similar kind of trend. Of course, the gigi number shoots up because of the large message sizes, both on this cluster as well as this cluster. And here, again, we can see like around 8 kilobytes or 512 kilobytes, significant benefits we get. And here, we get around a factor of 2 improvements. Okay, because as the message sizes are becoming bigger and bigger, the network becomes the main bottleneck now. Now that is only the latency, but what matters is the transactions per second, because many of these environments are not like trying to satisfy individual requests, but they are trying to satisfy a lot of these requests at the same time. So the main thing is, okay, how much transactions we can try to have at any given point of time. So here it says like with 4 clients or 8 clients. So if you see, these are actually the verse level design, and you will see that they are significantly higher compared to all other designs. Okay? And here we can, on the IB QDR, we can go almost like 1.4 million transactions per second. Okay? With like the small data size, with 8 clients. So this is the number. And here we try to scale it up to like 1,000 clients. And here, of course, we had to use some threads, so that's why you see the little bit of difference. Up to 8 clients, we had only 1 threads on different nodes. Okay? But after that, because these are multi-core environments, we started putting those threads on the same nodes. So that's why you start seeing the performance a little bit drop from 16 onwards. But in the end also, you'll see that we are able to sustain like up to 1,000 clients, almost like 600 million transactions per second. Oh, sorry, 600,000. 600,000. So then what we did is, like MPI, if you remember, I introduced our hybrid design, like the car with gas and electric. So we said like we can also have the hybrid between RC and UD, and this is exactly the same design. We took it here, okay? Because we had both RC design and UD design. So the idea here is to give similar kind of performance, but with a reduced memory footprint. Because as you are increasing the system size, you don't want even just like the MPI footprint to be minimum. Here also we want the Memcached footprint to be also minimum. Okay? And here, like if you go through like a 1 gigi or like IP over IB, we see almost like a 620 megabytes kind of memory footprint. But with our UD design, we have been able to significantly reduce to around 200 megabytes. And then as the number of clients increase, we have the different thresholds to switch between RC and UD to make it make it the hybrid, so that the hybrid line is the one here, which caps it around like the pure RC. If you do, again the memory footprint increases. It's just like similar to the MPI stack. So that's why we need to have both combination so that we can cap the memory. Then we took, so those are all micro benchmark numbers. Then we started going up just like the MPI. I mean, you try to do the initial micro benchmarks and gradually you go up, and then the goal is to show the end application. So here there is a publicly available something called a Olio benchmark. So that is a combination of like get, set, put, all different kinds of operation which mimic the real Memcached load. And here again we saw this kind of a benchmark. Here like it is showing 1, 4, and 8 clients, and here we are showing up to 1,000 clients. And here we can say like up to 1,000 clients, both the RC, UD, and hybrid, we are able to do very, very good, almost like 4 times better than the IP over IB for 8 clients. So this is the kind of numbers we see here, and it also the hybrid scales very well up to 1,000 clients. So then we wanted to move a little bit to the upper layer to the real application workload. So here we worked with a collaborator at Yahoo. Of course, they cannot give us their end application, but they tried to help us with their advertising application, and they had a miniature version of that, and they gave it to us. And so here, again, we tried to run that with all these HTTP, IP over IB, then our 3 OSU designs. And here again, we see that we can, with our designs, we can significantly beat all other solutions. Even the same network, instead of IP over IB, you can get almost 12 times improvement. Okay? And that is expected because we are really trying to run it with the lowest layer of the InfiniBand, which is the burst layer. We have done the designs. And the hybrid design again achieves comparable performance to that of the pure RC design with the reduced memory footprint. And we have like 2 papers here. One we presented in the ICPP, and this one just got accepted, will be presented at the CC Grid 2012 in May. Any questions on the Memcached side? Okay. So now let's move to the HBase. Okay. So the HBase, again the same question we asked, because once we had done the Memcached, we started asking the question, so can we take the current design like from the sockets instead of like putting it to the InfiniBand bursts? But here the problem is more complicated because of the Java. Okay, because this all Hadoop framework, as I mentioned earlier, has been written with Java, and Java, as you know, like I mean, there are all kinds of like garbage collection. There are byte streams which are going. So you need to design this in a very optimized manner. So what we did is, as an initial step, we took the JNI interface, that is the HBase like is making calls. There is a JNI interface, and we took that JNI interface, put our design over InfiniBand bursts. Okay, and the similar kind of environments here we tried to evaluate like the same 2 clusters we had, like a DDR and QDR, and here we did a small scale studies, like there was a name node, HBase master, 3 nodes were used, data node and region server, and node 3 was client. And once again, these are the pure open source version. We used the Hadoop 0.20, HBase 0.9, the Sun Java SDK, and here also we tried to isolate the disk accesses from the network. So whatever the mem table, that again we made sure that we contain in the memory. Okay? And later on I'll show you the HDFS part, which we are working separately to accelerate that, and then we'll put them together. And these are some very details if you want to reproduce some of these things, like the HBase operates on the key value pair. So we have a key size 20 bytes, value size is either 1 kilobytes or 4 kilobytes. The get operation, once a key value pair is inserted, we make sure that it remains in the memory, and we repeat just like the standard benchmarking technologies. We eliminate some of the warm-up times, and then take the average and report. So I don't want to go into details. You can take a look at this. Now here if you see some of the numbers, again we are trying to compare. This is like the IB DDR cluster. So this is the 1 gigi. Here is the IP over IB. This is the 10 gigi, and this is our new OSU design, which is the green. And the left-hand side is trying to say how much time it takes, and the right-hand side is the throughput in terms of the operations per second. Okay, and of course there is a correspondence here. So here you will see that we are able to, for 1 kilobytes HBase transaction, we are able to do it in a 65 microseconds, and here we are almost like 15,000 transactions per second, and 4 kilobytes we have 88 microseconds and around 11,000 transactions per second. And compared to 10 gig E, this is like is giving around factor of 2 improvement. This is DDR, and on the QDR here, similar kind of trends we get. Of course, the same operation because the QDR is faster. We are able to reduce the time and also push the throughput here. We are able to go up to 22,000 TPS and 16,000 TPS, and we compared to IP over IB, we show factor 4 improvement here. The same trend continues. So those are for get operations. You see the same trend for put operations. The green lines, if you see, we are able to reduce the latency and then push the throughput. And here we see around like 34% improvement compared to 10 gig E. And then on the IB QDR side, it's a factor of 2 improvements over IP over IB. Now then what we did is, once we did some initial design, then we started asking the questions, can we really see where we are gaining or where we are losing? Okay, so we did a very systematic analysis, like each of those timings, we tried to break down into all these components. Okay, so in the HBase framework, together with the Java, JNI, at all the different layers. So there is a client serialization, client processing, server serialization, server processing, communication preparation, and then communication. Okay, and we tried to do a very systematic measurement for HBase put 1 kilobyte and get 1 kilobyte data, and the broad things what we had expected, and that's what we actually validated, that is the communication time. So this is the top part, which is basically we are trying to reduce compared to this time, which is a 1 gig E, IP over IB, 10 gig E, we are able to reduce it significantly using our Warp's design, and this is where we see the big benefits, and all other components more or less remains the same. Okay, and the same trend also continues with the HBase side. So if you just take the communication time, which is this top part, so here you will see that like it is a 8.9 microseconds. There is a factor of almost 6 improvement at both sides. Okay, so this is what we are saying, because we are working on the networking part. I mean, that's the best what we can achieve. Okay, it's just like the parallel application. You can optimize on the communication, but computation time also comes into picture. Okay, and that you can only accelerate by faster processor or accelerator. Okay, you cannot like use a better network to reduce the computation time. You cannot do that. Okay, and that's what we are seeing, and especially since the stack has been designed with the Java, it has overheads. Okay, and if a C version has been written or somebody writes a C version, life will be much more easier. We can even push the performance even far better, but at this time that is not done yet. Okay. So this one actually will be presenting the paper at ESPA's conference in May this year. So then we had like those are micro benchmark numbers. So here we actually run a single server with multiple clients, because the HBase you just don't do like a single server, single client. There has to be multiple clients. So here again, like the number of clients, we increased up to like 16 clients here, and we are showing the time and operations per second, and almost similar like 4 clients. Here we get like this is our design compared to gig E to IP over IB and 10 gig E. We are able to reduce the latency and also increase the throughput. So here we are able to go up to 50,000, 53 kiloops per second with 16 clients. So if you compare with 10 gig E, so this is around like 27% improvement. And then there is actually a Yahoo Cloud Service benchmark, which is available openly to evaluate different kinds of HBase implementation. So we actually took that workload, YCSB read-write workload, and here again we see almost like we try to increase the number of clients up to 128 here. So if you take some of the data here for 64 clients, we get almost like a 42% improvement compared to IP over IB. Or the HBase gate latency also similar, like 40% improvement. So we have just a paper got accepted at the IPDPS 12 So this is in the month of May. Again, we'll be presenting the detailed design and the numbers there. So finally, let me come to the HDFS side. And here, if you remember, like this is the file system side. So this is like the HBase and the Memcached. We try to keep the data in our memory. So we are purely focusing on like the network level operations. So HDFS, we wanted to a little bit go into details and saying how the network is interacting with actually the storage subsystem. So we did two kinds of designs. So the first, we tried to study like the impact of hard disk drive and SSDs for HDFS. Okay, and this was actually, the study was done later, like our first study, we started with that, but I'm showing that number later on. And that was very interesting. I'll show the numbers. And then once we saw that, just like the HBase and Memcached, we have started working on, these are some preliminary designs. So this is not the complete design. So we are again taking the HDFS level operations over the verse. Okay. And here again, some of these, the similar kind of experiments and the similar platforms. So let me show the first set of numbers. So this was like in the HDFS area in the Hadoop, there are some standard benchmarks called DFS-IO, write operations. Okay. So here what we did is like, and traditionally these are the applications at the HDFS layer working on large amount of data. So we moved from like 1 gigabytes to 10 gigabytes. And this was like totally unmodified Hadoop. Okay. So we are not doing any enhancement. So we used 4 data nodes. And we tried to do the study saying we are not changing anything, but just only these data nodes, hard disk drive versus the SSD. Okay. And then trying to see whether the networks have an interplay there or not. Okay. And the results are very interesting. So here if you see this, the 1 gig with hard disk drive, so this is trying to show average write throughput. So the higher is better. So 1 gig with hard disk drive, so this is the lowest blue line. And with SSD also you get a little bit benefits, but not much. Okay. And that's what actually most of the people saw, saying, yeah, look, 1 gig. Then if you try to do similar kind of experiments with IP over IB hard disk, again this is the green line, you'll see that is not much difference. Okay. Now let's take like a SDP stack with hard disk drive, the same thing. There is not much difference. And 10 gig with TOW with hard disk drive, that also falls here. So all of these fall very closely here. Okay. And in fact people have shown, some other people say, look, HDFS layer high performance networks doesn't matter. Okay. So because the reason is not high performance network, the reason is the hard disk drive is the slowest one there. Okay. So these experiments, what we did is exactly same things we try to change. Now instead of hard disk drive, we try to put the SSD. Okay. And now you can see that you see the difference in the throughput. Now suddenly all these numbers go up. Okay. Because the end file system operations you are trying to do faster, and then if you can pump the data faster, you should be able to get the better performance. So these lines, if you see here, the same like IP over IB with SSD, now it comes here. SDP with SSD also comes here. 10 gig TOW with SSD also comes here. Okay. So this is with the DFS-IO write. Then we have a random writer. That is also another application. Comes with this Hadoop framework. And same trend we saw, like 2 data nodes. These are the hard disk numbers. This is the execution time. So the lower is better. So here we are able to SSDs we are able to do better, and it almost improves execution time by 50%. But if you go to more number of data nodes, now you try to see the more benefit. Okay, because the SSDs you are able to write faster, so that the network you can pump data faster, then you see the benefit. And here we see almost like around 59% benefits. Then there is a Hadoop sort benchmark. So that is even like a common example of we are trying to do the sort on a large amount of data. And there also we saw exactly similar trend with 2 data nodes and 4 data nodes is the execution time, the lower is better. And then the lower numbers are all with SSDs compared to these are like the hard disk. Okay. And we had a paper in 2010, we demonstrated these. So the goal, the lessons we learned from here saying that, look, you need to study both these things together. Okay. Otherwise you will not see the big benefits. It is like, let's say you want to design a freeway system, you can make the lanes 12 lanes or 14 lanes, but your exit lanes or ramp lanes are only one lane, that becomes your congestion point. Okay, the similar kind of things we are seeing here, because in the end the data is being synced to either to hard disk. So there, if you do better and better enhancements, then the high performance networks actually helps. Okay. Of course, I'm abstracting it a little bit, but typically these operations go through file systems. There are a lot of kernel calls, so all those things need to be evaluated to make sure that operations is totally optimized, and then the network will give you the benefit. Okay. So that was the first phase of the work, and recently we just started a preliminary design here, just like what we did with HBase and Memcached. We said, yeah, there is a data part we know, but even this network part, can we enhance here? So the exactly same question we asked, saying, okay, can we do the HDFS lowest level with the JNI interface? Can we have our OISU design which will run over the verbs? Okay, instead of going through the traditional sockets. So here these are very preliminary numbers. I mean, we have not published anything yet because the design is not complete, but initial numbers we are trying to show here. Again, the file size is changing from 1 gigabytes to 5 gigabytes. And here you see that the 1 gigi numbers here, this is the time, so lower is better. This is IP over IV, this is 10 gigi, then this is our design. So here we see like around 20% improvement over IP over IV and 14% improvement over 10 gigi. And these numbers are with hard disk drive, so we have not taken the corresponding SSD side. And as we analyze this data, means we find out more and more. I mean, a lot of stuff is happening. I mean, the way the Hadoop has been designed, it is like the fundamental assumption has been that it will run over gigi. Okay, so there are a lot of in between internal knobs which has been set to control the rate at which it moves. Okay, so it is like you design something which will run in a slow network. Now we are trying to take it to a high performance network. So each and every component of the design we need to reevaluate. Okay, because otherwise, like we might be accelerating some path, but then some other paths are choking. Okay, so this will still take us some more time to analyze all these paths and then make sure that all the bottlenecks are removed, so that it can actually run faster with the high performance network. So with this, let me conclude here. These are the initial kind of numbers. What we have done, especially on the HBase side, the research was especially done with funding from IBM. So they wanted us to explore the HBase design there. So to conclude here, as we saw, like the InfiniBand with RDMA feature is gaining momentum in the HPC system with best performance, greater usage. And so the question what we are trying to ask here is that, is it possible to use the similar kind of features and designs to accelerate the big data processing? And here I outlined some of the challenges and also showed some of the initial performance numbers. But what I want to stress is that this is just the initial tip of the iceberg, what we are looking for here. And as I introduced in the first slide, I mean, MPI and file system have gone through almost 11 years of research on the high performance network. So this is just like 6 months, 9 months of research. So there is a lot of stuff needs to be analyzed to really push this into the frontier, and especially here to take advantage of the high performance network, multi-core technologies, as well as the emerging storage technologies. And to stress that factor again, so let me bring this slide. So what we have done here is just touch this point-to-point communication only, and a little bit of I/O and file system. That's why I show the dotted lines. Okay, so this is a big framework here. For big data, we need big research. Okay, and that's what we'll be trying to achieve over the years, and hopefully by next year we'll have much more results, stronger results. I'll be able to say. So with this, let me conclude. Today I'm ahead of time compared to the last two presentations. So I'll be happy to take questions. Yes. Let me put it in two different manners, because many of these things are, unlike MPI, I mean, these things are very closed working, like all these companies, they have their own internal things and all. Other MPI and all are very open source, people talk about this. many years back, we did a lot of work on data centers, like the traditional data center, almost 4 or 5 years back. We tried to explore a lot of these components, but we were never able to put them together. Okay? So we restarted this research, especially the Hadoop became open source. Okay? So I think the one of the main important thing is that unless some open source module is available, which people can use for research and then so, otherwise I don't know what is happening in the IBM Inside or HP or SGI. I'm sure everybody is looking at this. There are big challenges, but all those knowledge remains within that company. So because we are able to do some of this open source work, I hope we can bring out these challenges, and then people will also realize that they are